but we run hundreds and hundreds and hundreds of simulations per evening.
Exactly.
Okay. All right. And so, and we don't advance something to on-road testing until it's cleared a lot of cases, right? Till we're very happy with our regeneration cases that apply to the feature being tested, right? So that you have that aspect of being able to just run the simulation much higher rate, right? You also have when it comes to long tail events, the ability to alter the frequency of long tail events. Okay, events that will rarely occur in the recorded data, right? You can alter the frequency at which those happen to provide more training and testing samples.
Right.
We're going through something absolutely historic.
Technologies across the board are growing exponentially.
It's a disruption that's going to completely redefine the way businesses compete.
In the next decade, we're going to lose 40% of today's Fortune 500 companies.
The exponential growth of computing is continuing.
AI is nowhere near its full potential.
Whether you like it or not, that the future cannot be stopped by anyone.
Hi there, everybody. This is Mark Verbenkov, and welcome back to the Future Tech and Foresight podcast. This is episode number 125. So as many of you listening are probably already aware, the first 100 episodes of this podcast really focused on automation, and specifically how it was impacting jobs. I have talked about autonomous vehicles a number of times. I think I've only mentioned autonomous trucking here and there or in passing on the podcast. So I'm really excited to look at autonomous trucking on today's episode, as I think it's quite an important subject that we all should be a little bit more aware of. And here are a couple ideas as to why we should be more aware of it. So really everywhere that you go, whether it's a local grocery store or a large shopping mall, there's one thing that kind of stands true between all these things, and that's the goods you have seen have most likely been on a truck. The vast network of roads, highways, and even truck stops can really be seen as the lifeblood of most modern economies. Trucking doesn't just bring us our favorite products, though. It creates jobs, fuels businesses, and you can say quite literally keeps our world turning. So as important as this industry is, it does have its fair share of safety concerns, due primarily to the excessively long hours worked by the typical trucker, but also changing weather environments and a number of other issues that we will touch on today. But as technology has been rapidly evolving over the last several years, there is kind of a new chapter on the horizon for the sector, autonomous trucking, which is the focus of today's discussion. So today, on this episode, we're really going to be looking at how autonomous systems are kind of getting married to trucking. So we'll be understanding the intricacies of developing self-driving technology, specifically for trucks, and how they differ from their smaller urban vehicle counterparts. I think the differences are pretty stark and quite interesting, and we definitely get into that today. So we're also going to be looking at what level 4 autonomy signifies, the foundational role that simulations play in perfecting these systems, and this is something that I wasn't fully aware, and I was definitely happy to have my guest on today to expand my understanding of just how important simulation plays in the sector. And of course, the kind of broad scale implications on employment, safety, and how we are going to be envisioning the future of transportation. So to guide us on this journey, I'm thrilled to have an expert who has really been at the forefront of these innovations. This is Robert Rossi. So Robert is TuSimple's Senior Vice President of Autonomous Systems. He brings extensive experience in leading AI on autonomous systems, leveraging his engineering and business leadership experience at Microsoft and TomTom. At Microsoft, Robert led a successful international standardization campaign for JPEG XR, which was a high dynamic range image coding technology. He led the core media processing team that delivered image, video, and audio experience for Windows and Xbox. Before joining TuSimple, Robert was Senior Vice President of Engineering for Autonomous Driving at TomTom. So Robert holds a Bachelor of Science in Mechanical and Electrical Engineering from Michigan Technology University. I think that Robert really sheds light on some of the fascinating aspects of autonomous vehicle technology in today's episode. And for me, anyways, clearly lays to rest any doubt as to specifically how this technology might be so much safer than the current human drivers. Great. Hi there, Robert. Thanks for joining me on the podcast today to talk about autonomous vehicles and trucks specifically.
I'm looking forward to it, Mark.
Great. Well, yeah, thanks for coming on. So the very first question that I ask every single one of my podcast guests is, what made you get interested in the autonomous vehicle trucking space or in the technology that you're working on? So maybe we can just start right there.
So I think the origin of my interest goes back longer than most people in the field. I worked at General Motors in high school.
Okay, wow.
At the tech center. And they talked about a vehicle that they had made that was autonomous using radio frequency communication back in the 50s. And I worked in the division that worked on the first industrial applications of robots that were stationary, doing things like spot welding. But we did implement a couple autonomous robots in the factory to move really heavy equipment around. In fact, Volvo made them, and they followed a wire in the ground. And I was kind of became interested in the whole concept of things that operated autonomously at that time. A couple of years later, when the PC era kind of boomed, there was a book called Brains, Behavior, and Robotics by a guy named James Albus out of the government agencies. And that book was what really inspired me to become interested for the length of my career in advanced artificial intelligence, especially applied to autonomous robots.
Awesome. That's quite an interesting far back experience that you had. Was that first autonomous vehicle, was that one that was going around a track?
Yeah, it was an oval track.
Yeah,
right?
Yeah. I've read about
it. It was highly structured, right? So it was an autonomy solution that was infrastructure to vehicle dependent.
Right. Very interesting. Yeah, okay. I have read about that one before. I don't know if I touched on it on the podcast or not, but interesting that you were working with there. So why don't we dive into like the value of autonomous vehicles at a general level here? So I've talked about autonomous vehicles before on the podcast several times. I've had a couple guests on it, but we haven't really focused on autonomous vehicles with regards to trucking. So maybe you could just kind of lay out kind of the value or the benefits that would be achieved or experienced by a society or a city that would implement and adopt autonomous trucking, kind of at a general high level for the audience.
I think it's actually not the city that benefits.
Right.
Okay.
Right.
It's the interconnectivity between the cities.
Yes.
Right. And so the real advantage of trucking deals with the fundamental problem of fatigue and the truck driver's needs to go to the bathroom, to sleep, to maintain their concentration at very high speeds with very high weight vehicle, right? Different things like that. Those considerations are heavily kind of oriented toward long haul backbone type of freight. Okay. The long roads between cities. Okay. I still think that the tactical delivery in the 1 mile to 5 mile range in the hinterlands of the average city is still a great candidate for human piloted vehicles and trucks. Yeah.
Right. So it would be like a lot of the safety considerations, right? I think everybody's read, any listeners read about, truck drivers working, double or even triple shifts and falling asleep at the wheel, and kind of autonomous vehicles or autonomous trucking solutions would solve one of those issues.
And it also fundamentally alters that equation requires a truck driver to sleep after 11 hours of operation. Okay. Right. And so then, they're on the road, they're sleeping in the cab, right? They have to break their trip up over 2 to 3 days. Right. And it's not the most desirable mode of trucking. Okay. It's not a good quality of life. You can't go home at night. But there's a bigger factor of trying to maintain your concentration, okay, and your attention, okay, for long sustained periods of time with very little novelty on the roads. Right. It's just the human brain fundamentally wasn't designed to process information at 70 miles an hour, even in a car. Okay. Right. Our visual system wasn't designed for that depth calculations, different things like this, right? So yeah, I mean, on the long haul, that's where we focus, right? On long haul freight, this is a better modality in our view, okay, than human piloted trucks. It's safer, it's more fuel efficient. It has a variety of advantages over human piloted freight.
And maybe we can dive into a little bit of those other advantages. I would also assume that if I remember correctly, there's also a lack of truck drivers in various.
That's a different thing, you know. Yeah. So right now there's a shortage of 80,000 to 100,000 truck drivers, and it's getting worse. Okay, if the economy was humming better, it would be even more exaggerated, right? There's also pressure on the entire intermodal freight system for just in time, or, you know, one click purchasing kind of on Amazon and delivery tomorrow, right? Like it's highly integrated and optimized logistics. Okay. That's another pressure. Then the third thing is that new entrants, which would be new younger people, right, entering the field, have heavily distracted attention by the current technology trends with devices and so forth, right? Yeah. So that's leading to a higher degree of crashes and incidents in the younger drivers that are piloting.
Yeah, no, that absolutely makes sense. You know, I wanted to ask you about this later on, but to me, it sounds like the fears of autonomous trucking taking over truckers' jobs, based on what you were just describing, are not really warranted. Because if there's such a shortage, I'm sure that autonomous trucking vehicles would be able to fill that shortage while still enabling human drivers to do their work, and maybe doing their work a little bit better and at not such a harsh conditions.
Right. So when you this is historic, right? Every case in history kind of proves that type of hypothesis wrong. Right. Okay. So for instance, if we make the backbone more efficient, we lower the cost of freight. Okay. If we take the vehicle out, we lower the cost of freight. What does that do? That increases the purchase velocity, okay, of different products, right? Which requires more flow and more distribution in the endpoints. Right. So almost everything, every technology innovation that ultimately leads to lower cost, okay, increases overall jobs.
Right.
It's just a redistribution. It might be a little bit different, okay, in terms of how those jobs are mapped. You take from one area, but you increase in another area, and then there's a net benefit.
Right. Yeah, but people only think about, well, autonomous trucking job, you know, equals no job. So I think the calculation is a little bit more complicated.
Yeah, and what is a famous story about John Henry and the railroads?
Yeah.
Right. In the 1800s. Right.
Yeah. Exactly.
Thing, right.
Yeah.
The same thing about automobiles versus horses. Right. So these come and go, and each time it's disruptive. That's what people are uncomfortable with, right?
Yeah, of course.
There's an existing scenario, it disrupts it. The disruption causes some stress, okay, for the people that are in the, basically invested in the current mode, okay? But the world moves on, right? And the pressures that we face also bring new challenges and new technology solutions.
And hopefully for those people that are concerned about their jobs, more interesting jobs that they can do, right? You're able to, instead of focusing on one area for, you know, hours and hours at 70 miles per hour, you're able to do it, I don't know, maybe something a little bit more cognitively challenging, which is, I think, more interesting for people.
That's exactly it, right? Yeah. And so if we take that long haul driver and they become a more local delivery type person, that's a very dynamic, okay, and task orientated thing that's far better match for, you know, the human mind.
Yeah.
Okay. Right. Yeah. There's novelty, there's events, there's people interactions, there's all kinds of things.
Yeah. Terrific. Why don't we switch gears here a little bit? Let's talk about so you mentioned it, but maybe we can dive deeper into it. You mentioned the differences between kind of urban or intercity autonomous vehicle functioning versus long haul trucking. You know, I would assume I've done some work on autonomous vehicle projects when I was living in Europe, And one of the things that kept coming up in these, whether it was dealing with inner city shuttles or vehicles in general, is just the amount of chaos that happens in a city.
Right.
Compared
That's
to, I guess, what you guys are working, which things are a little bit
That's
simpler.
right. They're two different problems
Mhm.
with different hard aspects and easy aspects. Okay. So in the city, first of all, you got pedestrians everywhere. Okay. Right. So the interaction with humans that are, moving at a maximum of 3 to 6 miles per hour, right? They're everywhere, right? That's a problem. You have a ton of clutter in terms of vehicles, right? You have a lot of complexity in terms of intersections and odd dynamics of people and vehicles and the intersection signaling, different kinds of things like that. You have more sudden unexpected events. Okay.
Yep.
Although you have those on highway, but you have a higher frequency of them, right? And so when I looked at this field, first I started in full autonomous systems with aerial drones, autonomous drones. Okay. And then I did agricultural work. But when it came to vehicles, autonomous vehicles on road, I definitely was attracted to the trucking space because the on-highway challenge, okay, is more contained. Okay. Right. Then you have problems because you got an 80,000-pound truck traveling at 75 miles an hour, and you have to understand your environment at a much further distance, and you need to predict your environment much better.
Yeah.
Okay.
Yeah.
Then something that operates at a slower speed has more time to assess the scenario, right, or the situation, right. And so that's the one thing. The truck has some very specific and unique requirements for safety. One, the truck is wide and almost consumes the entire lane. Okay.
Right.
So the lateral interaction complexity is much more difficult than cars. Okay. That have more room laterally in the lane. Right. Secondly, to increase safety in the truck, you got to understand exactly where you are in the lane. Okay. If you can keep the truck perfectly centered, which is one of our key bragging points at Too Simple, then you can make very good use of the available room that you have to bias left or right in the lane, right? To give more room to a truck passing you by or an emergency lane vehicle on the side of the road, right? But you wouldn't necessarily have to have that level of sophistication in a car, okay, in a robotaxi scenario, right? So those types of things become factors. The next one is your perceptual system, right? In the robotaxi, the perceptual system is wide and not as deep. Okay. Right. So you're focusing on everything around you, but not as distant in the future because your speed is maybe 25 miles an hour or lower. Okay. Right. With a truck, you have two necessary configurations. One is very long longitudinal distance because you have the combination of the speed and the weight and the amount of time it takes you to slow the weight. Okay. Right. Which is greater than a car. Okay. It takes much more distance to slow a truck than it does slow a car on the freeway. Right. And then once you go off highway, you have this other capability of having to be able to assess in a wider field of view in a shorter range configuration, assess the environment for all of its complexities and be able to properly navigate in a safe manner. Right?
So what kind of technologies then are required for that to be able to happen? Like I know that there's been this debate for several years between, say, like Tesla's camera system and the laser vision systems of other vehicles for urban vehicles. But it sounds like you guys need a combination or some different kind of technologies to enable both a wide frame when you're doing those slower, arriving to distribution centers or places just outside of the city, but also the more depth vision that you guys need during the highways.
So the way we do that, so we have roughly 10 directional facing cameras. I think it's around 25 cameras altogether around the vehicle. But they have, basically the autonomous vehicle is much different than a human in that it doesn't have a head, neck, and eye, ocular motor movement, and all this kind of stuff that it samples the environment. So instead, we have a bunch of sensors that are fixed, okay, and they have different orientations, they have different depths, right, and that are scenario dependent, right. So we have a long range set of cameras that are also wide apart for stereoscopic vision. That's kind of helps you determine the depth 1,000 meters ahead of you. Okay, so our primary weapon all along has been cameras, very similar to Tesla. Okay, the secondary sensor has been LiDAR for us. Okay, LiDAR has its advantages and weaknesses, and we are seeing the onset of frequency modulated continuous wave LiDAR and radar, which can reconfigure between on highway long, narrow field of view, long distance, and the scenarios where you're off road, where you want the wider view. But the sensor combinations that we have are cameras, radar, LiDAR, ultrasonic sensors. Ultrasonic's really good for very simple calculation. Is there a vehicle next to me? Okay, next, the back of the cab. Is there something right in front of the vehicle? Different things like that. And so now the sensors are redundant in area, right? So they're overlapping. The field of view is overlapping between these sensors, right? So if one goes out, you still have 100% coverage, okay, by adjacent sensors, but they're also spectrally overlapped, okay? So the laser system, the radar, and the visible spectrum are all at different wavelengths, okay? And those wavelengths have different sensitivities to things like rain, fog, dust, different kinds of environmental scenarios, right? That make it difficult, right? And so basically, this combination of sensors gives you robustness against the environmental scenario that could be dynamic and changing, right? And make your perceptual system resilient despite these different conditions. And the key technology then that you have is an intelligent and adaptive fusion system, right? That knows which sensors are to be weighted the most valuable in the current environment scenario or the current condition, like there's mud on the sensors or there's dust or whatever, right? Which one should be weighted the best, and is your autonomy system in an operable mode, okay, given these environmental conditions, right?
Right, and I guess for trucking, that would be vastly more important because you're going through long distances where the environment is going to change much more substantially than in a city where, if it's cloudy or if it's foggy, it's going to be foggy more or less throughout the whole city, or if it's going to be raining, it's more or less throughout the whole city. But I guess for your vehicles, it could transition, multiple different kind of weather or environmental situations in one single trip. Yeah.
A single trip could be 1,000+ miles easy.
Yeah.
Right. It could be 1,500 miles.
Yeah.
Right. And so, you're likely to encounter all these different types of conditions, and the system needs to be resilient and robust to be able to continue operation. Otherwise, you're going to have vehicles sidelined all over the place.
Yeah. Oh, that's really interesting. That makes absolute sense. Maybe one last question with regards to the sensors. So I mean, of course, the sensors are getting better over time. Do you have a sense in, say, 5-10 years, based on your implementation and adoption of these sensors? Will there be needs for less sensors as time goes on, or is it because these sensors are getting better, maybe even cheaper, you can just keep adding new layers of these various sensors?
Well, let's first talk about the types of sensors. Okay, we're doing great with cameras. Okay, in the last couple of years, we've finally had high dynamic range imagers in the cameras, and now they're cheap. Okay, because produced in volume. That allows us to have a great range of sensitivity in nighttime and daytime scenarios, and wide range of lighting conditions, being blinded by the sun or being blinded by lighting at night, right? So the camera part is doing great. Okay. The LiDAR, the problem you have with LiDAR is the spinning LiDARs are not really a good solution for longevity. Okay. Right. It's a mechanical moving thing. And the rest of the design is trying to eliminate all mechanical moving parts, okay, due to the reliability factor, okay, right? And we've been promised from the ecosystem solid state lidar, right, which would have no moving parts, okay, for some time, right? But we are not getting the depth that we have, that we need, okay? It seems to be stuck under 200 meters, okay, 180 meters for solid state lidar, right? Now the up and coming one is solid state radar, okay, and that is increasing in resolution, in depth, okay, and reconfigurability between what I mentioned before, long range, narrow field of view versus wide range, short narrow from the same sensor, okay. So that's what plays out in the next 5 years is really going to be what is the dominance between lidar and radar, okay, and does radar kind of overtake lidar, okay. So yeah, the processing of radar is a little bit more indirect than it is with lidar. You just go straight to a point cloud, right? You resolve your point cloud, and then we do extraction, right, from that. Radar is a little bit more involved on the back end, right? Another thing we're likely to see is some dedicated processors that do post-processing of camera data and have that processing technology kind of pushed into the camera itself.
Very interesting. Yeah, no, that's interesting, because it sounds like as time goes on, which is, I guess, typical with any kind of technology, right? You have the reduction in costs of the peripheral technology, but at the same time, you have the robustness of your technology increase, right? So many of these concerns of whether it's the environment or whether it's, being able to see far enough ahead to tell your system to brake, it sounds like this is just going to get easier, cheaper, and more robust as time goes on, making these autonomous vehicles much easier to be deployed or adopted in certain regions.
There's another element that I kind of thought about before this meeting. You have this tricky interplay. So when we talk about timeframes, you have now till 2026, then you're going to have a period between 2026 and 2029, where we actually have a chassis designed by truck manufacturers to support L4 base truck platform. Okay. So and then after that, we have to bridge to a full production OEM built truck. Okay, right. That's 2030 and beyond, right? The OEMs will completely build the truck at that point in time, right? The interim window, the other problem that you have, right? When you start, you have more sensors because you have a higher failure rate, okay? And you need more redundancy, right? You actually get better reliability when you go to high volume manufacturing, right? So you could consider that the goal is to get to the point where a single OEM can commit to building 10,000 trucks, okay, based on L4 technology. When that happens, they're able to purchase the 10,000 batch sizes of, and maybe for cameras, it's 100, it's a lot more, right? They can have 10,000 batch sizes, which allows you to do very high quality manufacturing processes and methods, fixturing, different kinds of things like that, right? So when we start off like we are, we've got stuff that's hand soldered,
right.
Okay. And some of the components, right? Undesirable scenario, right? And we'll move to small lot manufacturing. You still need more redundancy in your sensing, right? Because you'll have, still have moderate failure rates, okay? But ultimately, to answer your original question, when we get to the OEM scale, there could be far less sensors and far less need for sensor redundancy in the system.
That's really interesting. Yeah, that makes total sense. You don't even need for the technology to move that far ahead. It's the economies of scale. I hadn't thought about that before. That's fascinating. Really interesting. How about level 4 autonomy? Shall we move into that?
Sure.
So I know I've talked about it on the podcast before, but maybe you can just quickly define what it is and then say how your organization is bringing trucks to that.
Okay. So first, L4 autonomy is not full autonomy that L5 is. Okay. L5 would mean the vehicle go on the road with some kind of vague notion of an origin and a destination. Okay. And without a lot of help, navigate its entire way there. Maybe the simple type of stuff that we have with Google Maps. Okay. Right. And pilot itself based on its full reasoning and processing capability contained in the vehicle. Okay. L4 is more of a structured kind of transportation technology. Okay. Our vehicles require a map, a high def map. Okay. That offloads a ton of processing that you would otherwise need to do to figure out what is the speed limit, what is the lane structure, what is the traffic signal to lane alignment, right? A lot of different types of interpretations. So with L4, you have this combination of offboard technology that does pre-computation, okay? And that can be ranging from simulation to mapping to any kind of testing, right? That we do, right? And then a delivery of a autonomy software release, right? That leverages this kind of information like the pre-computed map, okay? In performing its duty. So that's the differentiating thing about L4 is that it still, has this reliance on offboard technologies.
Right.
Yeah.
So, how far away are you guys from achieving that?
From L4?
Yeah.
So we're in the, if you consider it like a football game, right? You're in the red zone somewhere. Okay. Right. And the last 20 yards is, 80% of the effort.
Right.
Okay.
Right.
Right. And so, there's several big challenges that we need to solve. And I kind of outlined these for the company earlier this year into 12 fundamental problems that we need to solve.
Okay.
I'm not going to go through all those right now as it take too much time. But the key thing is you have to think back of what does that OEM need 10 years from now to build 10,000 trucks, right? Well, they need a successful decomposition of the technology that can be built by different suppliers who do different components of the solution, right? They definitely need that 3 years before, okay? And 3 years before that, they need to be convinced that there's a market big enough for them to build 10,000 trucks. Okay. Right. Some people think, okay, we're going to prove our L4 technology out by creating a commercial lane from Houston to Dallas. Okay. Yeah. Right. That doesn't do anything for the OEM. Okay. That could be a completely overfit, custom hacked solution that does that particular lane that is meaningless in terms of having a large enough operational design domain that you can sell 10,000 trucks into.
Right.
Right. Right. So you have to kind of stare down what are those problems that you need to solve, right? To get there. Okay. Clearly safety and reliability is at the core. Okay. So one of the things that we eliminated earlier in the year is let's not consider the possibility of if something goes wrong with the truck that it could stop on highway. Because in my life, I've never seen a truck just come to a stop on highway in lane, ever. Okay, right. And the only time I've ever seen a truck stopped in the lane is it's in an accident. Okay, right. So we got to eliminate that from consideration. What does that mean, right? And so there's a huge part of this that says, okay, maybe you're getting premature in the AI technology. You still have some key problems that you need to solve there. But what is the systems technology that you need to design to allow you to have a fairly operational system? Okay, right. So we call it supporting Byzantine failures, which is like a stochastic failure that could happen anywhere in the system. So you want to say, can I assume that a software error could happen? We cannot ensure millions of lines of code doesn't have an error in it. Okay. Can we have a hardware failure anywhere in the system and have it still remain operational? Right. So these are the true realities in engineering that you have to face to say, what is the necessity to build a product that's trusted by people, okay, on highway carrying 80,000 pounds at 70 miles an hour? What are the guarantees that we need about its primary behavior and its secondary behaviors and its backup systems and so forth to be able to accomplish this mission despite the events it could face along the way.
Yeah, that's an interesting point. How have you seen the maybe societal shifts in acceptance of this technology? Right, I think several years ago there was kind of exuberance of autonomous vehicles, specifically within urban centers, and there might have been a little bit of hesitancy with some of the earlier crashes being talked about or publicly pushed in media. But that's several years ago. What is your kind of general sense of societal acceptance of this autonomous technology now?
They're still going to be they're still going to be suspicious of the technology if there's evidence where the evidence points to the fact that it doesn't have a general reasoning capability.
Right.
Or you see what I'm saying? And
Yeah.
so a lot of this off-board computing stuff I'm talking about lifts the ability, the necessity, right, to have kind of deep reasoning architecture. By the way, the human brain doesn't have a lot of time to do critical reasoning at 70 miles an hour either.
Sure.
Right. That's the reason why insurance adjusters after an accident always tell you, were you familiar with the environment? Okay, that the accident occurred, right? Because that's the first indicator that the possibility of an accident scenario being your fault is possible, right? So yeah, I mean, you have to gain the public's trust. Okay. Now there's a couple aspects of trust, right? In a new industry, especially with artificial intelligence, there's a high level of secrecy, right, amongst the companies in terms of what they're doing, right? So we're not really offering the full transparency, okay, right, that would make them feel comfortable. And then secondly, the government agencies that could regulate this do not know enough about how it works, to regulate it. Right. And so they're not getting the assurances from government. They're not getting the transparencies from the companies involved. Okay. That's a problem we're going to have to solve. Okay. And also technically, there's been a lot of, defaulting to its black box, it's using deep learning as black box. Right. But there's a lot of work that we're doing and needs to be done to provide transparency into the inner workings to gray box. Right, what is now black box components of the system. Okay. And then also have defensible guarantees on safety in some of the sections of the pipeline where we can do that. So for instance, in the trajectory planning and the control part of that, we can implement constraints and we can provide transparency into what those constraints are. Okay.
Right.
Listen, in an emergency scenario, we will not jackknife the truck. Okay. We will stay inside these bounds of controllability, right? That will lessen, right, the risk of certain types of things occurring, period. Right. And so I think in the next 2 years, we have to make a lot of progress in that area. Okay. In providing that transparency, to providing better communication about how the thing works. Okay. Right. How it works maybe differently than how humans do the task. Okay. And ultimately understand what regulations and what constraints on the scenarios they operate in should be.
Right.
And we're getting some kind of inquiries right now. Like I've met with government agencies, the Arizona Department of Transportation, Tucson Department of Transportation, and they ask us, what could we do? Right. And we're like, the condition of the roads is an issue.
Right.
Gigantic potholes. Okay. And then the alignment's off on the vehicle and we think it's the calibration that's off or whatever. We notice scenarios like a truck going through a non-signaled intersection, trying to make a left-hand turn. Okay. It's very risky for normal truck drivers. And then we have mathematical proof, right, that's the intersection should be a signaled intersection, right? So there's certain types of adaptations, I think, that are pretty simple. Paint the surfaces on the road, keep them maintained. Okay, we have to interpret those, right? There's different kinds of negotiations by all parties involved, but I think that's what needs to take place before we, I would have to err on the side of the general public right now and saying, I can understand, I can empathize, right? Why they're nervous about this.
Sure.
Okay.
Sure.
Right. And then we need to do our job.
Yeah. Yeah. Well, it sounds like there's a significant amount of variables, right? Moving pieces, if you will, in order for that safety, that sense of security for these new kind of technologies, specifically this one, to come about. I know that you wanted to talk about simulation. So how would, say, simulation maybe, so to start off with, maybe we can talk about simulation, then we can get into like how that would support the I guess feeling of human beings and the society of accepting this technology.
So the first thing is, let's talk about the ways we simulate.
Yeah.
Okay. So the first method of simulation is simply to replay the actual on-road data. Okay. Up until the point of a decision or an action being made, because then the sensor data is going to reflect the action, right? But it's normally what you're trying to debug in the system is what was the interpretation of the sensor data right before it made an action that turned out to be undesirable action. Okay, right. So we have 20 petabytes, okay, of accumulated on-road data, 10 million miles plus, okay, of on-road testing that we've done. Okay. All of this is indexed either by comments that the test engineer in the truck makes, okay, or particular types of events like harsh braking, okay, right, and rapid accelerations or unexpected movement in the steering wheel of a high rate. So, and that entire amount of data is queryable and then able to be pipelined into a simulation engine to get results. Okay. Right. This is a very, very powerful thing at TuSimple, right? Very, very powerful asset that we have, right? So we have that fundamental capability. Then when we get down to debugging something, and a lot of times it comes down to, was a requirement of the system underdefined? Okay. Right. And a lot of this is, since it's new, right, you're discovering the details of your requirements as you go along, right? As you test, you have a basic design of the requirement, an analysis of the requirement, and then you have the nuances that come up on the road, right? And so one of the powerful aspects that we have in simulation is we can reverse engineer the real scenario into a synthetic scenario. Okay. Once we have the synthetic scenario, we can do counterfactual analysis where we look at other kinds of decision points. What if the vehicle we were merging against was going 5 miles an hour faster or 10 miles slower, right? What would have been the implications of our stuff, right? And so through that analysis and reasoning process, which could be automated in the future, okay, we then can fine tune and adjust our requirements, and then ultimately test the solution against those requirements. Okay, so that's a big thing. We can also put the entire truck in the loop. We have a truck behind our building that's up on blocks, right? Or we can run a simulation and test the control against the actual vehicle, right? It's called hardware loop. We have components in the loop type simulation that we have. Okay. And I marked down a couple kind of scenarios. So we talked about real world data experiences. You could also synthesize, we could augment the real data with other real data. So I could augment the real on-highway data with a pedestrian walking in the an emergency lane. Okay. So we can synthesize real data. Okay. Augmenting real data. Right. Of course, we could do that with the reverse engineered synthetic thing. Right. So you have this thing of taking, even if you had 10,000 cases, you do augmentation and now you got 1 million cases. Okay. Right. Through that kind of scenario. Right. We can also manually create scenarios. Okay. That might help us understand a generalization. Okay. Let's say a particular intersection types or something like that, a particular design that would help us test a generalized solution, right? Like maybe roundabouts or something like that. We also have the ability to automatically generate models. This is all called procedural generated content in the gaming world. Okay.
Right.
So statistically sample, Tucson environment or Phoenix environment, and then generate a city model, right? It has the same statistical characteristics. And then most important, a huge trend. So the area of the pipeline, when you talked about what areas are still heavily being worked on, okay, it's the prediction module, the predicted behavior of the other vehicles, and especially their behavior in relationship to ego, which is the truck, the autonomous truck. Okay. It's trying to change lanes. How are the other vehicles going to respond likely? And how do I know that if they're cooperating or not cooperating? Right. My intention. Okay. Right. And so an area that we keep chasing these things down, the deficits on a case by case basis. Okay. But I think the trend now in the industry is to go to generate traffic behaviors, okay, and use something that probably is going to be way beyond what you'll ever experience in real life, which will give it kind of superhuman kind of capabilities in behavior prediction of surrounding vehicles.
Maybe one step back. So your system, your AI system, do you have like multiple systems that these trucks are running on, or is it just the one too simple AI autonomous trucking system that these trucks are running through? Just so that I can understand.
We do have two separate technologies. Okay. One was largely developed in China, okay, which is an L2 plus system, okay. That is, given your emergency braking, your automated or emergency braking, your lane keeping behavior, it's more like a conventional L2 technology that you have, but using some of the technologies that we have in L4, okay, like long range perception,
okay,
system, and then the L4 technology is a single design, okay. It is a dedicated single architecture that we have. We have a couple different generations of hardware, okay, as we evolve in complexity and work our way toward lower cost, lower thermal requirement, compact solution.
Okay, super clear. So then all of this simulation data that you're not just generating but running through these AI systems in order to make them, I guess you kind of alluded to, like superhuman in understanding and predicting behaviors on the road. I think one thing that is still outside of most people's perceptions is how many loops these systems are able to do, like learning loops, comprehension loops that they're able to do in a span of, say, a day, right? So like a typical driver does, I guess, testing on the roads, and they do one, maybe two loops of testing throughout a testing day.
We have 5 teams. They do 3 a day, 15 a day. Okay. Yeah. But we run hundreds and hundreds and hundreds of simulations per evening.
Exactly.
Okay. All right. And so, and we don't advance something to on-road testing until it's cleared a lot of cases, right? Till we're very happy with our regeneration cases that apply to the feature being tested, right? So that you have that aspect of being able to just run the simulation much higher rate, right? You also have when it comes to long tail events, the ability to alter the frequency of long tail events. Okay, events that will rarely occur in the recorded data, right? You can alter the frequency at which those happen to provide more training and testing samples.
Right. Yeah. So one thing that might happen maybe just once in a trucking person's career, right? You can actually run that through 5 times a night if you want, so that they're very, very good. And therefore, I guess you could say superhuman when it comes to that event, if it even happens on the road. They've had all of this training data, all of this training experience that they're able to make a better decision than a human being would.
This is the optimal balance between, the simulated world where we have some advantages, and then there's no the areas where in the past people were focusing on, ray tracing and trying to simulate the sensors and all that kind of stuff. The giant win is in this area I was telling you about, the prediction layer.
Right.
Okay.
Right.
So there's also things you can do in simulation that you can't feasibly do in the runtime system. Okay. We could have a comprehensive physics model of the truck, okay, in simulation, right? And there we go the opposite way. 10 seconds takes the simulator an hour, okay, to run, okay, right? But it does it according to first order physics principles, okay, right? And then we test something like a tire being blown out, right? And we derive from that a successful reactive behavior that does not have a model behind it. Okay. It's just based on in this high fidelity simulation, we discovered that this particular technique, okay, of control, okay, would allow you to handle the blowout. Okay. Right. And then that is put as a rule. The truck doesn't understand how to do that on the fly. It cannot compute the first order dynamics model of physics of itself. Okay. Right. And the environment match and all that kind of stuff. But it does have the ability to say, I detect the tire blowout and I apply this rule. Okay.
Fascinating.
Right?
Yeah.
That's another key thing.
Right? Yeah, that's super, super interesting. I hadn't thought about that one before, but yeah, really fascinating, Robert. That's a very interesting point. I guess also one of the other questions that I had about these simulations that you're able to create, often a question comes up of how the human beings are going to be interacting with the autonomous vehicle, right? So most drivers are familiar with trucks on the road that are being driven by humans, and they're going to interact and react to those trucks in a very kind of specific way. But when there's an autonomous vehicle, they might not feel, I don't want to say comfortable, but familiar with an autonomous vehicle. So they might actually interact in a different way. But I guess you could run those differences through a simulator or through the simulation, so have the truck understand whether the human being is interacting with them as if they were a traditional truck versus an autonomous truck, based on, I guess, the understanding that you guys most probably have.
In late 2021, 2022, or January of 2022, we did our 10 Ghost Rider events where the truck was piloted with nobody. We have a famous video, it's inside of our company, of the driver of another truck having his truck in automatic cruise control, and then climb over into the passenger seat and stare into our vehicle because there was nobody in there, right?
Awesome.
He was totally freaking out, right?
Yeah.
And so these are new scenarios. And I know people going back to 2015 at Ford, actually, that were studying this kind of thing, is like, how are we altering the behavior of the vehicles around us based on their knowledge that, and the best thing is for them not to be able to detect that it's a autonomous vehicle, right? And then their behaviors are normal, and maybe they get adjusted to this over time, right? So I think that's that's a general part of that, but we do have to study that. So in normal simulation as it has today, compared to what we can do in the future on behavior generation, you basically have these things called behavior trees, and you model different stereotypical people piloting behavior. Okay. Drunk driver, distracted driver, granny, right?
Right.
Youthful driver, right? Somebody late for work, right? And then you have a behavioral model, and the nodes of the tree kind of relate to the context. Okay. Right. I'm late for work and there's a K intersection I need to get off on. What do? I speed up and I try to cut over 4 lanes at the last minute. Right. And so, but I think we're going to have to evolve those things to understand how people might react around and change their behavior if they do know it's a autonomous vehicle.
Yeah, very interesting. Well, I think for myself, having you speak about the issues, or about how simulation can essentially train your AI systems to specifically with the long tail issues, right? Or the long tail situations, you're able to train these AI systems in situations that normal truck drivers, human truck drivers might never even encounter, for me, helps me to accept the fact that, okay, these autonomous systems might be significantly safer in the coming years compared to your typical human driver.
Just so you know, we don't train inside the simulator today.
Okay.
Right. In general, in deep learning right now,
Mm-hmm.
there's going to be a transition over the next 3 years from supervised learning, which is done with a very regimented process of labeled data.
Mm-hmm.
Okay.
Mm-hmm.
Training of the system with labeled data or labeled cases, to self-supervised learning. Okay. Right. And then potentially reinforcement learning. Okay.
Right.
And that might be restricted to only parts of the stack. Okay. Which I believe would be control and planning, motion planning. Okay. That is the big opportunity for us to leverage simulation and kind of change the equation of on-road testing to offline testing. Okay. And then ultimately evolving simulation to be have a training capability as well.
So that's in the next couple of years. What other things, if we're looking kind of like at the future now, what other kind of things we've touched on, like the sensors, maybe some of the infrastructure might be able to change. You have the simulation. What are some other things that you're kind of looking out over the next 5 to 10 years that are outside of your organization? And then maybe we can also touch on, your roadmap and what you can touch, what you can speak to that Too Simple is doing.
So let me start with what we can do inside of our organization.
Sure.
And what the industry has to do in general. Going back to the problem that I talked about with the OEM needing to address a large operational design domain, like the bottom half of the United States. Okay. At least 30,000 miles of interstate. Okay. The one problem we have is deep learning tends to overfit to a particular environment. Okay. You run all day. We simply went the other way on I-10 in Arizona, right? From an intersection, went on highway one way versus the other way, and everything changed. Okay. The behavior of the vehicles changed because it was 2 lanes instead of 3 lanes, right? The road was paved differently, so it was crowned and it was wavy, right? Different kinds of things like that. So the long pull you have is, how do you generalize the technology, right? There's a lot of work going on in AI right now, deep learning, in combination of what I talked about in simulation called synthetic data, but also what they call transfer learning. And transfer learning and federated learning and something they call meta learning is all about the system having the ability to modify itself to adapt, okay, the current knowledge that it has to a new distribution of the input. Okay. Right. So you have these shifts in your distributions that characterize different things in your environment. Okay. And they shift as you move from state to state or along a long trip, right? How does a system not have to throw away all of its previous knowledge, start over and have a different configuration and a different instance of what it does now that the environment is changing? And what do you do when the environment is changing continuously as you're driving trip, right? So this is a big area that there's a lot of emphasis. The technologies are called transfer learning, meta learning, and federated learning. Federated learning, it says, once I've adapted in 15, 20 different places, can I bring all that stuff back into a foundation model? Okay, right? That makes the specific adaptations smaller until I come up with a completely generalized solution that fits all environments, right? So that's a big one, right? Externally, we have requirements. The whole ecosystem has to come together on this. Okay, they need to come together in timing, okay, commitment, okay, and who does what, okay, and we're the kind of partitioning the proper kind of coordination of the greater ecosystem. Okay. And without that being done, then you have certain companies that do the whole equation have an advantage. Okay. Right. And you'll see that as a business model picked by companies like Tesla, like Zoox, and they have full control over the whole thing, right? So they have less of a exposure to the ecosystem kind of coordination risk. That's part of the equation, right? So I think that's a part of it. And then I think the other external thing is the government, okay? Right? So the government doesn't know how to regulate, but it will regulate at a certain point in time, right? And so we're investing a lot of money, we're doing a lot of things, but we don't have constraints from the government right now because they don't know how to apply them. And then when those constraints do occur, they could train wreck us.
Right.
You know what I'm saying? And so this is kind of a similar scenario in the automobile in like the 1919 time frame, 1919, 1920, where just the safety aspects, forced the government reaction finally, right? People marched on Washington, due to the amount of traffic fatalities, different kinds of things like that, right? So anyhow, I think those are the key external factors that we need to ensure progress successfully.
Very interesting. Maybe then the final question is, and this is a bit of a random out there question, but when will we see, I guess, ubiquitous autonomous trucking let's say just in the United States? Is it going to take 5 years? Is it going to take 20 years? What's your...
Yeah, that's an interesting selection of time. It's not going to happen in 5 years.
Yeah.
Okay, right? And it will definitely be there in 20 years. Okay,
perfect.
Right? So the real timing that I tell everybody is for us to hunker down and focus on 10 years from 2023, 2033. Okay. And that being the starting point, you have 10,000 trucks built, okay, and operating on the road at that time. That's even hard to get to that date.
Sure.
You have to focus very, very succinctly in the 3, 6, 9 year time frame to hit that, okay? Because there's several decisions that need to be made 6 years before, 3 years before, etc. Right. But in terms of the alignment of technologies, the larger OEMs realizing that they either get on board and do this or they risk their whole business. And I believe several trucking companies will suffer, right? That react to this too late, right? But yeah, that's the time frame. I think they'll be on the road and they'll be operational, right? And then we'll have this phase between 2026 and 2029 where we have pilot fleets operating, right? In driver out, okay, in limited scenarios, okay, building up the final kind of priming of the ultimate network that you need to deploy these. And there's a lot of things the industry needs to do, right? You have to design the hardware for the current ecosystem to have parts like computer boards that they swap out and swap in, and the trucks going again, right? And who does that? Is it the existing truck component manufacturers, right? How do you realign the truck? It could be once a truck leaves the original facility, you may never see it again. It's just operating in a network, right? So you have these pull-in stations where it says, my sensors are out of calibration. I drive through this thing, I recalibrate, and then I continue on with my load. Right. There's just a lot of things that actually go into, but you have to project yourself out. And I say 10 years, and that's even pushing it.
Yeah.
Okay.
Yeah.
Right. But you have to project out, what does the world look like 10 years from now? And you have to imagine what 10,000 vehicles properly being supported, executing properly, their terminal interactions at the endpoints, right? All of this kind of stuff.
Yeah, all the infrastructure that needs to be in place.
All the infrastructure that needs to be in place. Yeah.
Super. Well, maybe I'll have to have you back on before the 10-year timeline, and you can readjust if
you have a lot of work to do.
Yeah. It certainly sounds like it. Great. Well, I guess we can end it there. Thanks a ton for coming on, and I hope that at the very least one person listening to this will get a better sense of just how much, I don't know if better is the right word, but how much a autonomous trucking system can be superior to a human driver if these kind of training, the simulated training and the simulations that are done for it can actually lead to, as you said, like a superhuman understanding of the environment. Because I certainly I think deepen my understanding of that capability. So hopefully another listener will.
I think in closing remark, people often ask me, how do you know when you're ready? Okay. And I used to say, when we can prove that we're the same capability as an expert truck driver, I actually think the world is going to hold us to a higher standard than that.
Sure.
Okay. Right. So we actually even have to aim beyond that, where it's for that scenario of long haul freight, superhuman capability.
Very interesting.
Okay.
Great.
Thank you.
Thanks, Robert. I'll have of course, the website up on the show notes for the episode. If you have another way, like say LinkedIn or elsewhere, where guests can reach out and or follow your work.
Yes, we have. We actually have a LinkedIn page for Too Simple. We have a Facebook page for Too Simple. Yeah, I mean, those are the best places to go. We also have YouTube videos of the actual driver out runs that we did.
Great.
Right.
Great.
So those are something where they can actually see the full promise, of the technology in action.
Great. Well, I'll post all the links up there on the show notes, and people can go check it out at their leisure. Robert, thanks again for coming on. Fascinating discussion. I think I'm going to have to ponder some of the things that you were mentioning for the next day or so. Thanks for coming on.
Appreciate the opportunity, Mark, and
Absolutely.
I look forward to talking to you in the future.
Terrific. Myself as well. Thanks again.
Take care.
Well, thanks for listening to this week's Future Tech and Foresight podcast. If you like what you've heard here, there are, of course, a number of ways that you can support the podcast. The best way would be to leave a review on Apple Podcasts or give a rating on Spotify, which you can find a step-by-step explanation for on the futuretechandforesight.com website. Alternatively, feel free to leave a comment either on the episode show notes or the YouTube channel where you can see video recordings of the interviews. And finally, if you are part of an organization that is aware of the disruptive and transformational impact that emerging and future technologies will bring and want to know more, please get in touch to hear about the strategic foresight services that we offer and how we can help future-proof your organization and take advantage of the phenomenal opportunities available to survive and thrive in the future.
A lot of future-shocked people and future-shocked institutions in our society are simply overwhelmed.
Once there is superintelligence, the fate of humanity may depend on what the superintelligence does.
Science fact is catching up to science fiction.
The first truly intelligent machine will be the last invention that humanity needs to make.
The only scarcity that will exist in the future is that which we decide to create ourselves as humans.
Within a 10-year design revolution, we can have all humanity living the highest standard of living anybody's ever known.
Progress is accelerating at an exponential pace, and it's going to reach a point where progress is so fast it's going to be a singularity.
We are probably one of the last generations of Homo sapiens.
Every single headline points to the birth pangs of a Type 1 civilization.